Hello students, welcome back to the classroom point. In our today's class, we are going to discuss one of the most important topic of the valence bond theory, that is overlapping of the atomic orbitals. So let's begin the class now. Overlapping of atomic orbitals. So let us see the definition of what is meaning of the overlapping of atomic orbitals. The meaning of overlapping is the partial merging of atomic orbitals having unpaired electrons with opposite spin is called overlapping of atomic orbitals. So, what is the partial merging of that two valence atomic orbitals of atoms having the unpaired electrons with opposite spin? So, let's take a particular atom. Imagine hydrogen atom is there, atomic number 1, electronic configuration 1s1, so that this hydrogen atom is having the one unpaired electron, and let us take one more hydrogen with 1s1 electronic configuration, so the atomic orbital must be half-filled, that too with the opposite spin. So when they come closer to each other to form a bond, the atomic orbital of both of these hydrogens, see this is the atomic orbital of hydrogen, this is the atomic orbital of the hydrogen. So they approach each other and the partial merging. So this area is called the common area or overlapping area. So this overlapping area is having the pair of electrons which are given by both of these atoms coming with opposite spins. So this type of the partial merging of the atomic orbitals of the any two atoms for the bond formation is called the overlapping of atomic orbitals. So in this overlapping of atomic orbital, there is a common area that belongs to both of these atoms. That area is called the overlapping zone, where it is having the pair of electrons are present. Pair of electrons. So that these pair of electrons are present between the both of the nuclei, hence these are called the bonded electrons. Or we can say that these are the shared electrons. So these shared electrons are experiencing the attraction of the both of these nucleus. That's why these shared electrons cannot be removed very easily. That's why we can say that the shared electrons are giving the stability to the molecule. Now, what are the conditions required for the overlapping of the atomic orbitals? So we know that atomic orbital basically is a wave function of electron. Wave function of electron, so that we can say that electronic wave function. So when electronic wave function is considered, so electron, imagine it is moving like this, which is electronic wave having the both positive and negative phases. The plus and minus represents the presence of the electron in the different phases. Means, see, this direction of propagation is same. imagine if you take the x-axis, both of these are moving in the same direction, but while moving phase oscillation, if electrons are coming one side, we are giving the plus sign, and the opposite sign we are giving the minus sign, so that they are moving like this. So plus and minus signs are given. So this plus and minus are not the charges of either nucleus or electron. They are just showing the information about the presence of electron on the direction of the both of the side of the axis, a particular axis. So which side these electrons are present. So now here, if atomic orbitals are considered, we know that s orbital has no direction. This is s orbital. It has no direction because it is spherically, shape is spherical, has no direction. And when you take the p orbital, plus and minus. So p orbitals has the direction. If you take this one as the y-axis, this is called the py orbital. And if you take this one plus and minus here, if you consider this is z-axis, so both of the lobes are oriented along the z-axis, so that it is called the pz orbital. And in case of the px orbital, imagine this is taken as the x-axis, so where plus and minus are present. So now we can call this one as the px orbital. So this plus and minus says clearly that here electron, this is the center part is called the nucleus. From the nucleus, this side electron density is present in this lobe, and this side electron density is present in the opposite side is electron density is present in this lobe. So one side if you consider as a plus, the other side must be minus. It is not compulsory to show this upper lobe as a plus. You can show this one also a plus lobe and this one as a minus lobe. So that here this plus and minus shows the electron density present on a particular side of the nucleus. So that's why atomic orbitals are basically represented using this type of the sign conventions. So these sign conventions are also known as the presence of the electron in a particular phase. If here and there electrons are present in the same phase, means only one side, either left side or right side of the atom we can consider it, but direction is different. Now let us see here how these atomic orbitals are going to overlap and what are the conditions required. This is the diagram of the atomic orbitals. Now let us discuss the conditions required for the overlapping of the atomic orbitals. Conditions for overlapping of atomic orbitals. The first condition is atomic orbital must have at least one unpaired electron for bond formation. The second condition is both atomic orbitals of bonded atoms must have unpaired electron with opposite spin. And third one, atomic orbitals or wave function of electronic wave. Wave function of electron must be in same phase and direction. So when we see this, based on the presence of the electronic wave function of atomic orbital, on in which phase and direction these atomic orbitals are present. So based on the phase and the orientation of the electronic wave, these atomic orbital overlappings are classified into three categories. They are, first one is positive overlap, or it is also known as in-phase overlap. So conditions for the positive overlap is both atomic orbitals must have same sign. This sign represents the in which phase the electronic waves are present. The second one is both atomic orbitals must be in same direction. And here z-axis is considered as internuclear axis. So let us discuss about what is the internuclear axis. If you take this is the nucleus of one atom, and this is the nucleus of another atom. An imaginary line that connects both of these nucleus is called as the internuclear axis. So atomic orbitals may overlap with each other along the internuclear axis or perpendicular to the internuclear axis. So this is called the perpendicular to the internuclear axis. So an imaginary line that connects both of these nucleus is called the internuclear axis. Now let us see in-phase overlap or the positive overlap. In this case, we must understand one more point, that s orbital can overlap any orbital along the internuclear axis. Reason for this is s orbital has no direction. That's why it can approach the internuclear axis from any direction. So let's have some examples here. First of all, when s orbital try to overlap with another s orbital, both must have the same sign, either plus or minus. That is what? Same phase. So this is called the SS overlap. This SS overlap took place along the internuclear axis, plus and plus. And if you take this is the PZ orbital, this is plus, this is minus, PZ plus S orbital with a plus, so that they overlap with each other. This is called the PZ-S overlap. Here also overlapping took place along the internuclear axis with the same sign convention. And p orbital can overlap with another p orbital. Plus, and this is minus. Now this is PZ orbital and this is also PZ orbital having the same side means same phase. So only positive phase are coming here. So positive phase same side, they overlap with each other. This is called the PZ overlap. So overlapping took place along the same sign convention. Imagine this is the px orbital plus minus again one more px orbital. When they overlap with each other, so this type of diagram will arise, overlapping. Now you can see this overlapped area is perpendicular to the internuclear axis. So overlapping is taking place in two manners. One is along the internuclear axis, another one is perpendicular to the internuclear axis. Here also positive sign lobes are merging with each other, partial merging, and negative side lobes also partial merging is taken place. Next, if you take this py orbital plus minus py orbital, when they overlap with each other, plus and minus. So here also this overlapped area is perpendicular to the internuclear axis. So this bond is py bond, and here the bond is called the px bond. Now the question is here, s orbital overlapped with the pz orbital. Can s orbital overlap with the px orbital and the py orbital? Yes, it can. Reason is here, imagine this is the px orbital plus minus. Now s orbital can approach this px orbital from the x direction with the same sign, so that we will get the plus and minus. This is called the s-px bond. Similarly, when py orbital, this is py orbital, try to overlap with s orbital, this is called the py and s bond. So here s orbital can approach the other orbital along the internuclear axis. The question is how here internuclear axis is present. See this here nucleus is present, here nucleus is present. See this overlapped area is present along the internuclear axis. Here also this is the nucleus. This is the nucleus. Now this is the common overlapped area that is located along the internuclear axis. So s orbital overlaps with other orbitals always along the internuclear axis, because s orbital has no direction, so that it can approach any orbital from any direction. But in case of the other orbitals like p orbital, d orbital and f orbital, they are directional in nature. Means in a particular direction these lobes are oriented. Hence these p, d and f orbitals or f subshells, they overlap only in a particular direction. When direction changes, overlapping do not take place. So in these cases, positive overlap, whenever sign is same, the overlapping is taking place. Such type of the overlap is called the positive overlap or in-phase overlap. In-phase overlap leads to the formation of a bond. That means here electrons are in the plus side, here also electrons are in the plus side. When electrons are in the plus side, overlap with each other, so there is a chance for the formation of the bond. If electrons are in the plus side here and electrons are in the minus side here, they cannot overlap. Such type of the overlap is called the negative overlap or out of phase overlap, that we shall see now. So what are the conditions to observe that negative overlap? Both atomic orbitals must have same orientation. Orientation in the sense direction. they must be located along the same direction. Atomic orbitals must overlap with unpaired electron, again with opposite spin, but with a different sign. Different sign in the sense of phase. Let us see here now. When you take pz orbital with another pz orbital, in this pz orbital, this is minus lobe, this is plus lobe, this is minus lobe, this is plus lobe, and the overlapping also taking place along the internuclear axis. But the question is here is, in the case of this pz orbital, electrons are in the plus side. In this case, electrons are in the minus side. So that I'll clarify this point very easily. See this, when both of these orbitals are coming from for the overlapping purpose, in one orbital electrons are in the left side, and in another orbital electrons are on the right side, then overlapping don't takes place because their phases are different. In both of the atomic orbitals electrons are on the same side, then overlapping leads to the positive overlap. If they are in the opposite side but that overlap takes place, the negative overlap, or it is called the out of phase overlap. But in this case also, but both of these atomic orbitals must have the same direction. That meaning is both must are in the same direction. For example, if you take the pz orbital, so this p orbital and this p orbital both are oriented along the z direction only, but the electrons presence is different. In one orbital electrons are in the plus side, in another orbital electrons are in the minus side, so that will not lead to the formation of the bond formation. Reason is, for the bond formation electron presence is compulsory. So here this overlap is called the negative overlap. Similarly, if you take the x-axis, px orbital, plus minus minus plus, so when they overlap, plus minus minus plus, this is also called the negative overlap. And if you take the py orbital, plus minus minus plus, so they also don't give any bond formation, plus minus minus plus. So this type of overlapping of atomic orbitals having unpaired electrons, but the unpaired electrons are in the different phases, that overlap is called the out of phase overlap or negative overlap. This will not give any bond formation. And next one is zero overlap. This is also can be considered as out of phase overlap. Then what are the differences and similarities between the negative overlap and zero overlap? In zero overlap, direction must be opposite. That means direction must be different. This is the only one condition that is required. Whether they are having the positive sign or negative sign is not a matter, but direction is different. Once direction is different, automatically bond formation don't take place. The reason is, if you take the pz orbital, in the case of the pz orbital, electrons are located along the z axis. So this is coming from the bond formation. But if you take the px orbital, in px orbital electrons are located along the x axis. So when they approach each other, overlapping do not takes place, even though overlap takes place, that is called the zero overlap, because in px axis electrons are in the x direction and in the pz orbital electrons are in the z direction. So once the direction is different, that type of the overlap is called the zero overlap. Now let us see here. Let us take a p orbital, here nucleus is present, and s orbital is coming for the overlapping like this. This is zero overlap. Because orbital cannot overlap with the nucleus, orbital has to overlap only with the electrons. So that's why this is called the zero overlap, which don't give any bond. And in the same way, plus and minus sign, imagine this is px orbital. This is also plus and minus sign, but this is a py orbital. This overlap do not give any type of the bond formation, so that they remain separately only, plus minus plus minus. Even though the phases are same, but overlapping do not takes place because the orientation of the electrons are in a different directions. So this is the type of the overlapping of the atomic orbitals: positive overlap, negative overlap, and zero overlap. Now let us try to see what is happening if the electrons are orbitals are overlap along the internuclear axis and perpendicular to the internuclear axis. This type of overlapping can be classified into various categories. SS overlapping. The condition for this type of overlapping is they must have the unpaired electrons with opposite spin, as well as they must have the same sign. So that means this type of overlapping we are discussing for the positive overlap. So in positive overlap, the first one is SS overlapping. When one s orbital overlaps with another s orbital, that overlapping is called the SS overlapping. So this SS overlapping took place along the internuclear axis. Whenever the atomic orbitals are overlapped along the internuclear axis and the overlapped zone is exactly located on the internuclear axis, such type of the bonds are called the sigma bond. So this bond we can call it the sigma SS bond. Next one, SP overlapping. In this case, s orbital overlaps with any of p orbital along the internuclear axis, giving SP bond. In this SP bond also, since the overlapping took place along the internuclear axis, this bond can be called the sigma SP bond. Third one, PP overlapping. So this PP overlapping is of three categories are there: PZ overlapping, PX overlapping, PY overlapping. So as per convention, let us consider the z-axis is the internuclear axis. That means whenever PZ orbital overlaps, it results the sigma bond formation. PX and PY orbitals overlap perpendicular to the internuclear axis. So that's why the bond resulted from these overlaps is called the pi bond. So now let us see here. PZ orbital plus minus PZ orbital, they overlap along the internuclear axis. Plus, this is minus. So this bond is called the sigma PZ bond. PX orbital px orbital when overlap. So this overlapping took place perpendicular to the internuclear axis. See, this is the nucleus here, and this is called like the internuclear axis. Now the overlapped zone is present above and below the internuclear axis, making the 90 degrees angle. Such type of the bonds are overlapping which took place perpendicular to the internuclear axis, and the bonds are called the pi bond. So that this bond is called the pi px bond. So this pi px bond can be represented as, imagine these are the both of the nucleus. Electrons, positive lobes overlap like this, and negative lobes overlap on the bottom side, plus minus. That means here, in case of the pi bond, electron cloud, that means a bonded or shared electronic cloud, is present above and below the internuclear axis. So above, that means away from the nucleus. And in this case, overlapped zone is located between the internuclear axis, that means close to the both of this nucleus. So in the case of the sigma bonds, nucleus concentration on the bonded electrons is more. That's why sigma bond is always stable. In the case of the pi bond, since electronic cloud is located away from the nucleus, so nucleus attraction power over these electrons is very less. Hence, a pi bond is called the weak bond. That is the reason why we need more energy to break the sigma bond and less energy to break the pi bond. Since less energy is required, pi bonds can easily participate in the reaction than the sigma bond. So we can say that pi bond is more reactive than the sigma bond. Now, let us take the py overlap. This is called the py overlap. Now let us see the difference between the sigma bond and pi bond. The first point is, it is stable bond, and this is unstable bond. Sigma bond is strong bond. Pi bond is a weak bond. The question is, why sigma bond is strong and stable bond? Because sigma bond is formed along the internuclear axis, so that nucleus concentrations are more over the bonded electrons. Hence, it gives the stability as well as the strong strength to the bond. So, this is taken place along the internuclear axis. Overlapping took place along the internuclear axis, and in this case, overlapping took place perpendicular to the internuclear axis. Since it took place along the internuclear axis, bonded electrons experiences more nucleus attraction power. And here, the electrons are located away from the nucleus. Since electrons are located away from the nucleus, they experience the weak or very less nucleus attraction power. And sigma bond always exists independently between any two atoms. First, sigma bond is possible. Only after formation of sigma bond, pi bond is possible. The reason here is, In case of the sigma bond, both of these nucleus are approaching, orbitals are approaching along the internuclear axis. Afterwards, partial merging take place. Once a partial merging takes place, this partial merging will bring the both of the atoms as much close as possible. Then only both of these orbitals which are oriented perpendicular to the internuclear axis, this direction px, py direction, then they will get the chance to overlap. That means pi bond exists only after the formation of the sigma bond. But sigma bond can exist independently, pi bond cannot exist. Pi bond formation takes place only after the formation of the sigma bond. So that here we can write down that it exists independently. This one do not exist independently. So first sigma bond formation takes place, then only pi bond formation takes place. And next one is only one sigma bond is possible. Only one sigma bond is possible between any two bonded atoms. But what about this one? More than one pi bond. More than one pi bond possible between any two bonded atoms. Let us take an example. Carbon-carbon single bond means the single bond is always sigma bond. Carbon-carbon double bond is there means one is sigma, one is pi bond. Carbon-carbon triple bond is there means one is sigma, two are the pi bonds. So only one sigma bond is possible between any two bond atoms, but pi bonds are more than one is also possible. In the case of the triple bond, the middle one is sigma bond and lower one and upper one called the pi bonds. Here one is sigma, one is pi, and here only sigma bond is present. And next here, rotation around sigma bond possible. If only one sigma bond is formed, then if atoms are located like this, we can rotate both of these atoms like this, up and down. So that we can rotate the atoms, because single bond can be rotated. But when pi bond is formed, see, this pi bond means you cannot rotate both of these bonds. The reason is, if you try to rotate both of these carbon atoms, so there is a twisting of this pi bond. They twist so that it will restrict the rotation of the atoms. So that here, free rotation is not possible. In sigma electrons don't participate in the conjugation. These electrons do not participate in conjugation. But these electrons, pi electrons, participates. In conjugation. Why pi electrons participates in the conjugation? Reason here is, pi bond is formed away from the nucleus, which is not strongly attracted to the nucleus, hence this is a weak bond. Hence the pi electrons always ready to jump from one place to the another place when the molecule is in the conjugation. That's why pi electrons participate in the conjugation, but sigma electrons usually do not participate in the conjugation. So these are the differences and similarities between the sigma bond and pi bond. Now let us see what are the factors that influence the strength of a bond. So let us see how the overlapping is influencing the strength of a particular sigma bond. So here is strength of sigma bond directly proportional to the extent of overlapping. extent of overlapping of atomic orbitals. This extent of overlapping again directly proportional to the directional nature of atomic orbitals. That means the orbital in which the electrons are oriented in a single direction, in a particular direction, so they leads to the formation of the bond. Their overlapping will be more. Such type of the overlapping is called a strong overlapping. So when the strong overlapping takes place, automatically bond formed is also to be strong. Now let us see here which orbitals are having the direction nature. P orbitals, D orbitals and F orbitals have the direction, because in P orbital Px, Py, Pz possible. In D orbital we know that the 5 orientations are there. In F orbital 7 orientations are there. So when the number of orientations increase, again the electron density in a particular direction gradually decrease, because the electrons has to be dispersed among all these axes. That's why overlapping do not give a strong bond. That is the reason why when P orbital overlaps in any sigma bond formation, that gives a strong sigma bond in comparison to the bond formation resulted from the overlapping of the either D orbitals or F orbitals. And what about the S orbitals? S orbital has no direction. Since S orbital has no direction, its overlapping is very weak. That's why the bond resulted from the formation of the SS overlapping is weaker than the overlapping takes bond formed from the P orbitals and the remaining orbitals. Now let us see here. Example, when the value of principal quantum number n increases, the strength of the bond decreases. So that we can write down that 1 overlap is more than the 1-2 overlap, which is greater than the 2-2 overlap, greater than the 2-3 overlap, greater than the 3-3 combination. So when the value of n gradually increase, the extent of overlapping decrease. When extent of overlapping decrease, automatically strength of the sigma bond also gradually decrease. So let us take an example here. 1s2p overlap is stronger than the 2s2p, which is stronger than the 3s3p. So we have taken the only sp combination, but the value of n when increase, strength of the bond gradually decrease. There is one more reason also. When the value of n increase, the electrons are located farther from the nucleus, so that nucleus cannot concentrate on the bonded electrons, hence the strength of the bond will be very weak. Then next one is, what happens when the value of principal quantum number is same? So if n is same, then it depends on the direction purely. So that here you can get the P overlap gives stronger PP greater than PS overlap greater than the SS overlap. So that this we can write down as 2P overlap is stronger than 2S overlap, which is stronger than 2S overlap. Here one exception condition we have to discuss, that is 1S overlap. So 1S overlap is exceptionally stable despite not having the direction, 1s orbital is giving the two stronger sigma bond in comparison to the any of these sigma bond formations. Reason here is 1s is nothing but coming from the two hydrogen atoms. So hydrogen bond enthalpy is 435.8 kilojoules per mole, which is highest for any single bond between any two atoms in the molecules. So the strongest sigma bond is the sigma bond present between the two hydrogen atoms in the H2 molecule. So reason for this unexceptionally stability of the this hydrogen sigma bond in the hydrogen molecule is, in hydrogen molecule, the electrons are located in the 1s orbital. The 1s orbital is having only single electron, and so that the electrons are closer to the nucleus, so that nucleus power is too much heavy on the both of these bonded electrons, so that breaking of those bond electrons will be very difficult. Hence the sigma bond in the H2 molecule is too stronger than the any other bond. For example, if you take the 2p, let us take an example here. Hydrogen sigma bond is stronger than the chlorine sigma bond. Reason here is, here hydrogen bond is formed by the overlapping of 1s orbitals, here 2p orbitals. So in this way, when the extent of overlap increases, gradually strength of the sigma bond also increases. When it comes to the pi bond, so when it comes to the pi bond, so pi bond formation takes place by p pi overlap, which is stronger than the d pi overlap. So when the size of the orbital increases, gradually the pi bond strength decreases, so that p pi bond is stronger than the d pi bond. So dear students, I hope you understand this class of overlapping of atomic orbitals, which is the extended part of the valence bond theory. If you really understand my videos, please do like the videos and subscribe the channel. Thank you one and all.